to 5G Technology World. I'm site editor Martin Rowe. 5G base stations, large and small, convert RF signals to digital baseband. EdgeQ has recently begun sampling what it calls a base station on a chip. To find out how that works, we spoke with Vinay Ravuri, EdgeQ CEO. Vinay, thank you for meeting with us today. Can you explain the architecture behind the base station on a chip?
As a company, this is kind of how I describe it. You can think of it as like 3-layer cake of 5G or 4G. So at the bottom is the actual chip. It's the physical chip. And this chip is designed using RISC-V based technology. So it's very programmable. RISC-Vs are CPUs. We've modified them to be used in different types of environments: 4G, 5G, indoor, outdoor, private, telco, macro type of deployments, as well as there's some AI functionality. So that's just the CPU. By itself, it really doesn't do anything. It's not that intelligent. Really what makes it intelligent is this layer here. And in 5G speak, or cellular speak, it's called the PHY, but it is implemented using software. So we implement that using C and C++ that runs on subsequently in the RISC-V CPUs that are on this chip. And there's lots and lots of cores, which I'll get into. At EdgeQ, we not only develop this software, but we develop a carrier grade deployable solution, meaning it's not a reference piece of software. A customer can take it out of the chute, and configure it for whatever, and then boom, you have a base station on a chip. The last part here, this is this layer 2, layer 3 software. This we don't sell this ourselves. This is something that we partner with other companies. For example, Redis is one of the partners where we take their layer 2, layer 3 and integrate that. Typically, customers want to either use a third party for this or develop their own version of it. So that's what we do as a company, is deliver these things. What we announced this week, Martin, is that we're sampling this product. It's 3 years in the making. The evaluation card that we have already, in fact, sampled looks something like this. This is a cartoon version of it, but this big thing in the middle is really a heat sink. Underneath that is EdgeQ chip. That does baseband processing, and it could be based on software. As I said, it takes different forms, different functionality. One of them is a DU, distributed unit in ORAN speak. Another based on, again, firmware, same chip, same hardware. It could be an RU, radio unit, or you sort of combine these two and call that a G node B. In this case, it would be a small cell. And this is something that we been working on for 3 years, and we taped out the chip. The chip came back, looks rock solid, and we've sampled this to one of our early customers that we've been working with for almost 2 years now. It has not only Linux running on the ARM portion of this chip, but on the RISC-V, it has all the signal processing running. In fact, these waveforms were captured. Think of it as 5G traffic going through this chip and coming out on the RF, and out of the RF onto an antenna. So essentially, you're measuring things over the air, and the signal captured.
Does the base station on a chip have any RF functions, or is that done separately? Does it work only at baseband, or does it include RF?
So the chip itself, the single chip, covers the baseband. RF is a separate chip that sits on a board. Okay. We partnered with a company that works closely with us, but the interface between the RF and the baseband is open. There's something called JESD interface, so we can connect to an analog devices or a TI or anybody. But we closely partnered with a company called SiTune that does an RF, and this happens to be a SiTune chip.
So is the interface between your chip and the RF, is that analog or digital? Is it at transmit frequency? Is it at some IF, or is it where is it?
So there's two types of interfaces. So let me maybe go to the next slide. So you see this block here that says RF. So this is the RF section of the RF interface section of the chip. There are two types of interfaces to the external world. One is what's called JSD, which is a digital interface. Mm-hmm. Okay, and like analog devices, TI, they interface to baseband using JSD. So that's one way to do it. Another way to do this is we have ADCs and DACs on our side as well, which means that it would connect to an RF chip that does analog now. So that's analog IQ. So IQ symbols would come over, samples rather, would come from an RF into our chip. And then we would, on a receive side, convert that from analog to digital and then downsample it and potentially run, cleanup stuff and then bring it into baseband.
You talked about the PHY being on your chip, and the PHY can also has many components as you move from the RF to the baseband. And what happens, and since you're talking about being ORAN or Open RAN compatible, that means that the user or the carrier or the base station, whether it's small or large, there's this concept in Open RAN called a functional split, where depending on the application, you might put more of the PHY down at the DU or more of it up at the radio unit, depending on what you're doing. So how does that work here? Is that something that the user can program themselves through some interface, or is it something that is has to be sort of programmed into the chip?
So ORAN has first, they disaggregate the base station into an RU, DU, CU, as they call it.
Yes.
But then there is functional splits within that. In other words, where does the RU actually end its business and then hand it over to the DU? It can do, there's a very popular split called 7.2. So we support that. Now, the split is somewhat arbitrary for us because the PHY is firmware based, software based, which means that it doesn't matter if it's 7.2 or option 6 or option 8 or some other option, because we can take any one of them as long as the transport is eCPRI. Mm-hmm. And that is what we support. We support eCPRI as an interface into the ORAN RU-DU. If you're RU and not DU, then we would be talking to the DU over eCPRI, and same thing with we're DU and we're not RU ourselves. So 7.2 is what we sort of centered around because that's what most everybody's asking for. But it isn't limited to that. And there are options like, there are rather deployments like millimeter wave, where 7.2x is not feasible. You need to do more of that processing in the RU itself because the data rates become too high. In which case, we would become more of the RU than the DU in that case. So that would be, and for us, again, as I said, the function of the DU shifts into the RU. So, well, the split, just the PHY goes up all the way to the MAC layer, meaning the PHY finishes up all in the RU itself, and we would just become the RU in that case. Mm-hmm. So it's arbitrary because it's software.
Okay. And is that something that the customer has to specify that we're going to use this and that chip is in a sense programmed at whether it be at the factory, or some other place, which also leads to the question, if it is programmable in that sense, is how much of it is done at the factory, or is there something that or is it something that can be programmed sort of after the chip is, shall we say, a finished product, at least from a hardware perspective?
The software is always there. So we deliver, let's say, the full software suite to the customer. And then we'll say, okay, there's a nominal feature set, let's say regardless of the split.
Mm-hmm.
And then we will charge the customer on a what we call a subscription basis based on what features they actually enable. So let's say it's millimeter wave and it's got option something, okay? It's not that they have to configure. This is something that is so fundamental to the deployment that they would tell us this is what they're buying from us, because at the end of the day, the chip has to be capable in terms of its capacity for the bandwidth that they're looking for. So they would buy a certain type of chip from us, right? Meaning, performance of this chip is this high versus this high. And then they would pay according to that. It's something that they have to think through because it has implications on the routers that they have in between, has implications on how they provision things and the management systems that go with it. So it's not one of those things where they just go, well, this month will be split this and another month will be another split. It won't be that way. It'll most likely just be a split that they have pre-decided and then deployed according to that.
Okay. Now, you said that your chip can function as it can include the DU functions, or again, depending on how you specify the split, but you could specify the split in such a way that, if you go all the way to the other end, that yes, all of the DU functions that that the whole Open RAN is trying to disaggregate anyway. But if you wanted to, could you go back to the point where your chip is essentially the traditional BBU?
Yeah.
How much of that, and then my sort of follow-up question is, if you are separating out the DU, let's say the CU and the DU from your chip, do your customers then maybe go to a DU software vendor and a CU software vendor to take care of the rest of the Open RAN, of the rest of the access network?
Yeah. So we support these three modes. We support an RU mode, we support a DU mode. We don't do CU ourselves. So that would likely be some other company that would deploy. And it tends to be just general purpose x86 in the CU right case, by the way.
Right.
So we would interface to CU, but we wouldn't be the CU. The way we implement this third one here is we just take RU/DU software and fuse it together and essentially becomes one. So natively, we are an ORAN system. It's one chip here, another chip here. Here is just one chip where the software runs on the same chip instead of two separate chips. That is how we do. So this, now, the thing is the BBU, you can call this sort of like the BBU, but the difference is BBU has traditionally been in a macro base station, the large telco base stations.
Correct.
This is more like a small cell in that case.
Okay.
Here we could be in a macro environment, but when you combine these two, to put that on a single chip gets challenging because the number of users and all that stuff.
If you are building a small cell, generally, don't the small cells rely on a single DU somewhere, in the city or somewhere nearby, where one DU supports several RUs essentially?
A DU supports many RUs. That's right. What DU is.
Right.
A small cell is combining these two into one. So there is no supporting multiple. This goes all the way up to CU. So okay, the RU plus DU plus CU becomes a single small cell. Now, there is this new concept that people are playing around with, which is maybe what you're referring to. A bunch of small cells, which is essentially RU, DU plus CU, but then remove the CU portion of it out of the small cell and take a bunch of these small cells, which would then be called RU plus DU in one, and then aggregate a bunch of those small cells into a single CU.
Okay.
That is possible with us. Again, in that scenario, CU wouldn't be us, but in a scenario where all three are in one, that becomes us, because the number of users and the kind of traffic that goes through small cell is not the same as this gigantic 3-sector macro base station with 3,000 users. This would be more like, I don't know, 32, 64 kind of number of users. Small, tends to be small.
Okay. So, but the output, I'm calling it the output, looking towards the network side, not the RF side, of this small cell is most likely fiber, or could it be copper, or both, or either? And if so, how much, if it's, for example, if it's fiber, you're going to have to connect a driver to it. So I'm wondering what else, if you were connecting to fiber particularly, what else do you need to make that connection to go further up the network?
10 gigabits have two types predominantly today. One is there's copper 10 gigabit, and then there's fiber 10 gigabit.
Yes.
It just depends on the deployment itself. Like there may be buildings that already have a 10 gigabit twisted pair, then that's what they would use. If it has a 10 gigabit fiber already in the building, then they'll just use that. We support both.
When do you expect the base station on a chip to go into full production?
So typically, right, these things take about a year for customers to take the chip from you, and they go through their productization. It's really limited by them. That cycle is about a year. So our production cycle kind of aligns to that. So it's more like between now and mid next year.
Vinay Ravuri, CEO of EdgeQ, thank you for meeting with us today. For 5G Technology World, I'm site editor Martin Rowe. Thank you for watching.